Swayam Prabha. Digital India. Educated India.
Welcome back. Today we shall talk about predicate calculus, because we need to do predicate semantics. So first we'll do a very brief history of predicate calculus, and also I'll introduce the whole thing there. So a brief history, as I said. The Greeks, the ancient Greek philosophers, talked about logic, and there were two different groups that were working on logic in ancient Greeks. One was the Aristotelian group, and the other one was the Stoics. And the Stoic philosophers talked about logical constants such as and or and if then and all that stuff, but they did not discuss much about quantifiers such as all and some, as in all humans are mortal. The Aristotelian group talked about quantifiers. They worked a lot. So the entire Aristotelian logic is actually some kind of logic of quantifiers, but it does not deal with the logical constants such as and or. Leibniz tried to combine both, because that was part of his agenda, his lifelong research, but his effort did not succeed in creating a system of logic. Boolean algebra, once again pioneered by George Boole, deals with the logical constants and creates a system of logic that does not really deal with quantifiers. That means we can see that there were a lot of efforts, but at the same time nobody could actually combine the system where you have and, or, if then, neg, and you have for all x and for some x. So this was the problem for a very long time, unless until a very great logician appeared. So it was Gottlob Frege who for the first time succeeded in combining these two systems of logic, that is, the system that deals with the logical operators like and, or, and also you have quantifiers like some x and all x. In his Begriffsschrift, he actually combined these two systems and created kind of an integrated system of logic. But the problem was his system was very complicated, with very complicated notations and all that stuff. The works of Russell, Whitehead, Tarski and other great logicians have made today's predicate calculus possible. We shall follow the system presented in Kalish and Montague's Logic, Techniques of Formal Reasoning, that is this text. And so we could have followed some other system, but since we are doing Montague semantics, we somehow will follow the Montague system. So now we know that in Aristotelian logic we have 4 categorical propositions. So look at the first one: every cat is animal, no cat is an animal, some cat is an animal, and some cat is not an animal. So these 4 are categorical propositions. Why? So nothing else, no other combination is possible as far as the human logic or the human language is concerned. Why so? It is we talked a lot about propositions and all that. We also talked a lot about and, or, and all that stuff. We did not talk much about this every and some business. We need to do that now. Now there is one very important thing, that is, why is it that we cannot have any other variety? We have just 4 categorical propositions and nothing else. The reason is something like this. You see, there are 2 parameters here. One, the quality, and the other one, the quantity. What do I mean by quality? Quality is something like yes or no. So, when I say, so there are qualities of two types, one is affirmative and one is negative. So, all yes sentences are quality wise affirmative sentences, all no sentences are negative sentences. And also quantities or quantity is of two types, one universal and particular. What is the universal quantity? When we talk about all or none, see, in all these cases we are dealing with an entire group. When we say all humans are mortal, we are dealing with an entire group, the group of humans. Nothing, nobody is left out. We are talking about an entire group. So, such sentences where we deal with an entire group do have the quantity called the universal. Now, similarly, when I say no human is mortal, I do a very similar thing. Why do I do that? Simply because I am saying that no human is mortal. That means any human I consider, any human I can ever see is non-mortal, right, or is not mortal, which means that once again I am talking about the entire group, the group of humans. So, once again both these sentences, one is positive, that is, for example, take every cat is an animal. This is positive, but that is, this is affirmative, but this is universal. And the second sentence, no cat is animal, here this is negative, but once again this is universal, because I am talking, actually I am talking about all cats. I am not picking out one single cat and talking about it. And then I will vary the, so I first varied the quality, then I will vary the quantity. So, I will have this. So, this is affirmative when I say some cat is an animal, because I am talking about it is positive, it doesn't have any no in it. At the same time, the quantity is particular, because I am not talking about all cats, I am not talking the entire group of cats is not my concern. My concern is just, is just some cat, which means at least one cat. Maybe I am talking about one cat or 5 cats, but yes, I'm not including all cats in this group. So, here the quantity is particular, not universal. Similarly, here I am picking out some cats, not all cats, and I am making a negative statement. Since there are two parameters, quality and quantity, and since there are two values in each, we can have just 4 varieties. So, I can combine this two, or I can combine this two, or I can combine these two, or I can combine these two. That gives me just 4 categorical prepositions, nothing else. All other prepositions will be combinations of these 4. So, this is one assumption of our logic. Our logic will not deviate from it much, from this model much. So, so the first preposition is universal affirmative, I repeat. The second, universal negative. The third, particular affirmative, and the fourth, particular negative. Okay. Then now we will talk about the logical understanding of these prepositions. We can see that when we say that every cat is an animal, we are sort of in the modern in our modern understanding, we are kind of talking about 2 different sets, the set of cats and the set of animals. And in a sense, we are saying that the set of cats is actually part of the set of animals. And in the second, we are doing something very different. In the second, we are saying that the set of cats is not part of the set of animals, right, because no cat is an animal. In the third, we are saying that the intersection is possible. So, basically we are saying that we are saying that this is possible. So, that there is at least some member here, and in the fourth we are saying that that this is one set, the set of animals, and this is another set, the set of cats, and some cat is not an animal. So, here there are some members. This area does have some member here, it is not an empty set. So, this is what we are basically saying in these sentences. Now, if we want to understand algebraically, we are saying this: for every cat is an animal, we are saying that for all x, if x is a cat, then x is an animal. Now, you see, before Frege, nobody could combine. So, there are two different things. So, one is this if then, the other one is this quantifier for all x. Somehow you are bringing the idea of quantification here. Before Frege, nobody could do it successfully. Nobody could combine this all and if then. Now, what is it claiming? It is claiming that for anything, for all x, x stands for everything. X is a variable that ranges over everything. The point is, I may choose anything. If that thing is a cat, then that thing is an animal. So, what if that thing is not a cat? I do not consider it. I first choose it. If it is not a cat, fine. My theory is absolutely fine, because I claimed if it is a cat, then it has to be an animal. That is, my minimal claim is basically there is no cat which is a non-animal. This is what I am claiming in the first sentence, that there is no cat which is not an animal, right? And then we go to the second, and we will see what we are doing there. In the second, we are saying that no cat is an animal. What does it mean? For all x, whatever x I choose, if it is a cat, then it is not an animal. That means I will never find something that is at that is my minimal claim. My minimal claim now is I never find a cat that is an animal. Here I am not claiming that there are animals or there are cats. My minimal claim is I never find a cat that is an animal, or alternatively I never find an animal which is a cat also at the same time. So, the group of cats, if it exists, excludes the group of animals. So, there is no intersection of these two groups. That is my minimal claim, right. So, these two are very important thing. These two sentences never guarantee the existence of either group, right. So, I am not saying that cats do exist. That is why these are not existential sentences, because existence of any group is not guaranteed. Maybe both sets, the set of cats and the set of animals, are empty, but that is not my concern. But in the second group, that is, some cat is an animal and some cat is not an animal, I am doing something very different. I sort of guarantee that that there are two groups, two non-empty groups, that is, both groups do have members. Both groups do have members. So, here this is the group of cats and this is the group of animals, and at the same time they intersect. That is, there is at least one member which belongs here also and here also. Now, it is not just the common membership of X, it is also about the groups not being non-empty, the groups being non-empty, that I guarantee that both groups have got members, and not only that, there are common members, or there is at least one common member. This is the claim I make here. So, there exists at least one X. So, at least there is one thing which is at the same time a cat and an animal. So, and the second one, say the second of this group, that is the fourth sentence on the page, says that there exists at least one X such that X is a cat and is not an animal. So, I am saying that yes, both groups exist, this group and this group, both the groups exist, and both the groups are non-empty, that is they have members, and the first group has at least one member which is not a member of the second group. At least one member sort of resides here only. So, at least there is one exclusive member in this group and it does not go there. This is what I am claiming in the second sentence, and we shall see how we can logically translate these sentences into logical propositions, symbolic propositions. So far these are not symbolic, but we need to translate these. So, the translation for the first sentence, that is every cat is an animal, is for all x, if x is a cat. So, let us interpret C or C alpha as alpha is a cat. Let us interpret A alpha as alpha is an animal. Let us interpret, that is it, and the other things we all know, and sum x phi means there exists at least one x such that phi is true, and all x phi means for all x phi is true. Now, with these interpretations, let us try the symbolic sentences. For example, how to read this? For all x, that is any x you may choose, if that x is a cat, then that x is an animal. This is the first sentence. So, once again, this is true even if there is no cat. Now, you can compare this to a sentence like all trespassers will be punished. Now, this sentence is true even when nobody trespasses. So, the point is, if anybody trespasses, anybody, then that person will be punished. So, it is true. So, that is the reason all something in a sense means that there is no guarantee that both the sets, both the groups are non-empty, but if they are both non-empty groups, then if the first one, that is this group, if that has got a member, then that thing x will definitely be a member also of the second group. That is the whole content there. And then we shall consider the second sentence, which is no cat is an animal. Here I am saying that I consider every x, I consider every individual, and I find that it is such that if it is a cat, if it is a man, it is not my concern, but I check each individual. If it is a cat, then it is not an animal. If it is a cat, then it is a non-animal. This is what is said in the second sentence. Now, once again, the third sentence guarantees that there are two non-empty sets, the set of cats and the set of animals, and then it is saying that there exists at least one x that belongs to both sets. So, two sets are there, cats and animals. There is at least one x which goes there and which goes there also. So, as I said, and then yes, there are members here and there are members here also. The fourth sentence says that, well, once again, there are two sets and there is at least one x that belongs to this set, but it does not belong to that set. So, there exists at least one x. It should be corrected, actually there is one neg there. So, yes, so there is one neg there. There exists at least one x such that x is a cat and is not an animal. So, this is the translation. I write it again because there was a mistake, Cx and neg Ax. This will be the right translation of the fourth sentence. So, this is how we translate sentences. Then we need to consider kind of a language for doing proper predicate logic and for understanding it. Our symbolic system has got these elements as we have shown here. So, this is the language part. So, the system has got two different things. One, the language part, but that is not enough. Also, we need a language for talking about something, right? For talking about some model. We have seen that our semantics is model theoretic. Without a model, it cannot function. So, it is at the same time a language and also a system or a model the language talks about. So, we need two components. The first component is the linguistic component. So, these are the basic expressions of our language. Unlike English, these are symbolic. So, for example, these things, these basic expressions in English could be names, but here these are E, F, G, H, I, J. So, I have just chosen 6 names, and then these are all names, and then we have say 4 one place predicates. Like we know what one place predicates are. They are about one term, not about two things. They are not relations, they are just one place things, like D, C, A, M. They are like smokes, is good, and all that stuff, or sleeps. And the third component is the two place predicates. We just have one, that is L, and so it is a relation between two things. And then we have two quantifiers, all and some. We have the logical connectives, the logical constants we already know about, and now we need individual variables. So, we need variables like x, y, z and such. Ideally, we need kind of an infinite supply of variables, but it is enough to start with to have just two variables or 3 variables. So, we have chosen x and y, and we need the punctuations. They are all the brackets, the first bracket, the flow bracket, the square bracket and all that stuff. Now, we may translate. We are in a position to translate some sentences into symbolic sentences. So, then we go to the for the real translation, we also need to consider the model, because we need to check the we need to understand the translation. So, denotations of basic expressions, for example, let the denotation of small e be the capital E. You can see that all small letters have capital letters as their denotation, as here. So, small g and capital G, and let us assume that these are the capital letters are not letters. They are not any representations or they are not any symbols, but they are real individual. That is a very important assumption for any semantics. Denotations of one place predicates. So, the denotation of D or the reference of D is a set which consists of just 2 members E and F, and then the denotation of C is once again a set consisting 2 members G and H, and we interpret say D as dog and C as cat, and then A can be interpreted as animal, and there are 4 animals in our system which belong to the set of animals E, F, G and H, and there are 2 musicians in our system I and J. the names are different. So, basically I is small I is the name, and j is small j. So, and the denotation of the only one two-place predicate we have here is this. This says that if you interpret L as likes, then it says that I likes itself, j likes itself, I likes E, j likes F, j likes G, and E likes I. Nobody likes anybody else in this system. So, then we go to the translations, and we need to understand each and every translation and also their meanings. Now, every cat is an animal. In our system, we have seen is for all x, Cx implies Ax. No animal is a musician. That is for all x, any x you can choose. If it is an animal, then it is not a musician. Some animal is a cat, which is true. Then there, and also see, all these sentences are sort of true in our real model. And some animal is a cat, which is there is some x such that it is an animal and it is a cat. Some animal is not a cat. So, there is an animal which is not a cat. This is how we translate all the sentences, and we actually need to translate a few more sentences. So, basically what we are saying, if we want to combine the language along with the reality, perhaps it would look like this. So, when I say that every cat is an animal, I meant to say that for all x, if x belongs to the set of cats, then it belongs to the set of animals. We can check it here. Now, now you can see that anything that belongs to the set of cats. So, only G and H belong to the set of cats. Can we find them in the set of animals? Yes, we do find. Therefore, this sentence is true. It is a true sentence. Let us check the other one, the second one, which is for all x, if x belongs to the set A, that is the set of animals, then it does not belong to the set of musicians. Let us see. Now, what are the things that belong to the set of animals? There are 4 things: E, F, G, and H. Can we find any of these in this set? We don't. E is not there, F is not there, G is not there, H is not there. Therefore, this also is true. We can verify. We can verify almost visually. That is what we are trying to do. We are trying to combine the language with the model we have in hand. Now, the third sentence, that is, some animal is a cat. There exists at least one x such that it is at the same time, such that it belongs at the same time to the set of animals and the set of cats. Is it true? Now, look at the set of cats, which is G and H, and look at the set of animals, that is E, F, G, H. These two are things, right? So, if these are 2 common members of these 2 groups, cats and animals, right? So, that means that there is at least one thing. If 2 things are there, definitely there is at least one thing. So, if 1000 things are there, then also it is true that at least one thing is true, whatever. It applies to at least one thing. So, so there is at least one thing, say that is G, and also H is equally true. Now, that they belong to both groups, right. So, and the fourth one, that is there is at least one thing that belongs to the group of animals, but that does not belong to the group of cats. Now, you see among animals, E and F are such things. E belongs to the set of animals, but it does not belong, E does not belong to the set of cats. You do not find. So, this also is a true sentence. Both are true sentences. So, all the sentences we have translated here, all the symbolic sentences we have translated here are actually true sentences. So, we go to the next slide. Now, we may translate once again some other sentences. For example, we can now translate a sentence like some animal is a cat and a musician. How do we translate this? We are saying there is at least one animal which is a cat and also a musician. How do I translate this? I can say it this way: there exists one x such that it is an at least one x, it is an animal, and it is also a cat and a musician. Is it true? Definitely not. Not the way we have constructed our model. So, with respect to our model, this is a false sentence, but that does not matter. We are translating it. We are trying to translate it the way it is given. And suppose we have something else. All cats are, it is not true that all cats are musicians, if that is a sentence. How to translate? It is not true. It is not true that all cats are musicians. Basically, we are saying it is not true that for all x, if C x, then M x. So, we can see what actually the intuition here will be completely supported by the system and its calculations. What is the intuition? That we are saying in the sentence, we are trying to say it is not true that all cats are musicians. That is, there is at least one cat which is a non-musician, right. So, basically this tends to say that there exists at least one cat which is not a musician. We will see that there is a scheme, there is a translational scheme, there is some kind of calculations that will actually show that these are equivalent structures. We will not see much of those things, but some of those we need to see. So, yeah, this is how we translate several sentences, or you can try a sentence like every cat is either a musician or an animal. So, every cat is either a musician or an animal. How to translate it? So, every cat will be translated as for all x. If it is a cat, then it is either a musician or an animal, right. So, this is how we translate sentences. We need to do a lot more translations to understand what is going on. Now, this is not all, because translations also can be sometimes very complicated. For example, consider this sentence: every musician likes a dog. What does it mean? As a naive person, I may say that it means that every musician likes a dog. How is it that it has two meanings? But actually, this sentence has two meanings. How is it? One meaning is it may mean this, that is, there is at least one dog every musician likes. So, it is about at least one or more dogs. So, it is about a set of dogs every musician likes. So, it is something like this: there is a dog every musician likes, or maybe there are two dogs every musicians like. Maybe that is one interpretation. And another interpretation is every musician M1, M2, M3 or M4, everyone has got some dog they like. So, this is another picture. Now, we notice very easily that these two are not the same picture. Their translations are different. For this, it starts with some dogs, right? How to translate this? We just write there exists some x such that x is a dog, and for all y such that y is a musician likes y x. So, this is this picture, right. So, there is at least one dog. It can be D1 or it can be D1 and D, it can be both D1 and D2, but the point is, if somebody is a musician, then that person definitely likes D1 or D1 and D2, whatever, or D2, just D2 and nothing else. So, this is one interpretation of this sentence, and the other interpretation will be for all y, if y is a musician, then there exists some x such that x is a dog and L y x. Now, we can see that evidently these two are not the same translation. These two do not have the same picture. They do not represent the same content, right. They are very different in structure. So, yeah, this is how our logic can deal with ambiguities. So, the natural linguistic sentence, this sentence does have ambiguity, but the logical sentences we construct cannot have any ambiguities, right, because the very structure would be free of ambiguity, but we can do it in our own way. Then yeah, as I said, here I have already translated the sentences, we can just consider, and then some basic deduction, not that we will do all deduction rules and stuff, but we can do some very basic deduction so that we can solve some problems, very elementary deduction rules, so that we can see how prepositional calculus works, how the calculations or the computations in prepositional semantics work. So, for that we have these rules. The first, we are not talking about we are not maintaining the sequence. First, let us consider quantifier negation. Now, we can see that this part says that it is not the case that all x phi can be any sentence. Then this is equivalent to some x neg phi. We can check the intuition very easily. For example, as we already said, for example, say there is a sentence. It is not the case that all x, every human is a musician. So, we translate then, which is very true, which intuitively means that there are humans that are not musicians, right. So, if we say this, there should be some kind of a device to translate this part into this part. So, here is a device that will help us do that. How? Now, you see, first I apply quantifier negation on this. So, neg hx implies mx. 2. After doing that, I have, that means there is some x such that it is not true of it that hx implies mx. I just write one quantifier negation or qn, and then what do? I simply apply the denial of implication. We have seen that in the previous sessions, that this means, so as we said yesterday or in the previous session sometime, that what is the meaning of, it is not the case that when it rains the soil gets wet. It means only one thing, that is, it is raining, but still the soil is not wet. Nothing else is evidence against the rule that if it rains the soil gets wet. Similarly, here this is what is being asserted. This is saying that if x is h, then x is m. How do I deny it? The denial will be x is h, but not m, right. So, that is what we are doing. So, we are just writing here to denial of implication. We are denying the implication, and we can see that we have somehow reached this, which was our intention. We wanted to check whether there is a device that helps us convert that sentence. That is, it is not the case that all humans are musicians into there is some non-musician human. Now, this part of the rule which says that it is not the case that there exists x such that phi, which means this. Now, we check this intuition. Let us say something like it is not true that it is not true that some humans are magicians, say. So, once again H and M. So, that means we are saying that there is no magician. We need to there is no human magician, not that there is no magician, there is no human magician. So, so what is our sentence? Our symbolic sentence is it is not the case that there exists an x such that it is at the same time a human and a magician, right. We want to reach somehow, we want to reach that all humans are non-magicians, right. So, we want to reach for all x, if human x, then not magician x. We want to reach this, right. Let us try this, whether we can do this at all. So, yes, 3, I do quantify negation. By doing that, I am saying all x is such that h x and m x. So, I just say 2 q n and 4, I actually apply this on this. I negate, what is the rule I have? I have De Morgan's law, right. That makes it not h x or not m x, which is 3 De Morgans. We did this in the previous session, that we have justified the De Morgan's law in the previous session. We may refer to that, and now also we have seen that neg phi or psi is equivalent to phi implies psi. So, we justified this, we called it implication. So, we apply that and we get h x implies neg m x, right. I just write here for I. Here psi is neg m x, right. Psi is like neg m x and phi is like h x. So, the entire thing is psi. So, then it is neg phi or psi, which means phi implies which means yes, phi implies psi. So, this is what we have done. So, we can see that once again there is a route for reaching this from this. So, as we intuited, as we thought was possible. So, now we may see other rules. This is not actually a good set of rules, because this is very how to say, very basic, and because we are not supposed to, we don't have time to do proper computations and stuff, but still I think that we need to understand some basic applications, some basic computations for predicate semantics. So, the first rule is universal instantiation. So, there are not things of two kinds in predicate semantics. One is instantiation, where we conclude we get rid of the quantifier. So, getting rid of the quantifier is instantiation, and adding the quantifier is generalization. is generalization, so I and G. So, these are two different things, and quantifiers are of two types, either universal, which is all x, or existential, or some x, right. So, according to that, there would be 4 rules here: one, universal instantiation, universal generalization, and then existential instantiation, existential generalization. So, we see all, we at least try to see all 4 here. We may not actually have all 4. So, universal instantiation is this. This is actually very easy, because what is it? I just say that all x f x, that is anything you choose, is f. In that case, you can easily say, therefore, f x or f y, anything can come, simply because I said everything is f, right. So, you can see that it's now it will now help us work on some problems. How we'll see that. And then the second rule is the universal generalization, which is sort of complicated. We are not talking about all aspects of it. So, basically we are going to discuss an erroneous version of the rule, not the correct version of the rule, but still it will help us understand something. So, the point is, we need to show that all x, if human then mortal, if that is a show line, then we have to show, that is the rule, that h x implies m x. Somehow we have to do that here, and we need to work on it. We will see this, we will apply this and see how it works. And the third one is once again slightly complicated. When somebody tells me that there exists at least one human, how do I get rid of it? Now, how can I say that x is a human? The problem is, if somewhere I knew, somewhere in the previous steps, suppose somewhere else, if I knew that also x is a dog, what will happen is, if I just translate or if I just conclude h x, then I will be having this trouble, because then anybody can say that dx and h x, right. The problem is, how do I know that x is at the same time d and h? There is no way. I just said that there exists a human, and somewhere I know that dx, that is x is a dog. How do I combine the two? I should not combine the two. So, I should not know anything about the variable I get here. If prior to getting it here I know anything about this, then my conclusions will be wrong. So, that is the reason we need to follow some caution here. What is the caution? We say that when I conclude something from this, when I get rid of this, I must have a variable that is new. Why? Which is not used anywhere. It is something like naming an entity, and I must see to it that the name is a new name, that name is not shared, it is a unique name, like a password. My password cannot be somebody else's password. So, just to ensure that this y never happened before, we have this y as a new variable. So, this is the rule we need to have, and this is a constraint actually. So, this is a rule with a constraint, and then we have a very easy rule, that is, so these two are actually very easy, this one and this one, but these two are problematic for various reasons. A few we have seen. The existential generalization, somebody said that x is f. So, somebody said that there is a fact thing. From that I can easily say there exists a fact thing. So, adding the existential quantifier, I just say e.g. 1. So, adding the existential quantifier is actually very easy, but it is difficult to remove it, and on the contrary, removing the universal quantifier is very easy, but adding it is slightly trickier than removing it. We may now see some problems somewhere. So, problems in the sense we may see, we may solve, we may translate and solve some real linguistic problems. For example, consider this: all humans are mortal, and then all Indians are humans, therefore all Indians are mortal. So, we first translate it, break each and every sentence and translate. If you number them like this, it will be like this. So, 1, all humans are mortal. For all x, if human, then mortal. 2, this sentence, all Indians are humans. For all x, if ix, then hx. 3, we need to show that all Indians are mortal. That is for all x, if ix, then mx. How do I do it? Intuitively, we can see that this makes perfect sense, but then how to compute it? By using rules. We do it here. So, then we remember that in the previous slide we had this, that universal instantiation is this. This is how very easily we get rid of the universal quantifier, but this is how we add the universal quantifier. So, there are steps. I need to prove that all x phi, I need to first prove phi. That is exactly what we are trying to do here. We have another show line, which is show ix implies mx. We just write ug, that is we have to do ug. So, 5 can be ix, this is like the conditional proof we did. So, we assume that ix is the case. Somehow we have to reach mx. Can we do that? That is the question. So, we call it kind of an assumption. So, it is an assumption for a conditional proof, right, and we just assume that ix. Then we get rid of the quantifiers from these two. The first one gives us hx implies mx. I just write 1 ui, and then the second one gives us ix implies hx. I just write 2 ui, that is universal instantiation, which is an easy rule. I just get rid of the quantifier without having any trouble, and then 8. This is called the rule. So, can I show now this? So, I do it in steps. So, ix implies hx and ix. We can see that, therefore, it is modus ponens, right. So, modus ponens looks like phi implies xi, phi, therefore xi. This is modus ponens. If we remember, so I just apply modus ponens on these two. So, I just write 5, 7 modus ponens, and 9 I have human x, mortal x, ix. Okay, sorry, this is not. It will be hx. Yes, now correct. And then I once again do modus ponens on this too, because this is hx implies same form. Hx implies mx and hx. So I get mx. I just write, what did I do? 6, 8 modus ponens. So I wanted to reach mx. I have somehow reached mx. So I have shown this, right. So this is the assumption, and this is my shown thing. I could add another line here as 5 prime show mx. So actually that is the promise, that I will show mx, and I have shown mx. By doing that, I have shown the entire thing. So first I have shown this. So this is a feature of the Montague logic that we box a proof. It's actually it's very significant, and we will see some other time why it is very significant if we have time, but as of now we just assume that we have to do it. So, we prove something, we box the proof and scratch the show line. So, yes, this is how, by using very few rules, we have done this, and then little different thing. So, the first line is fine, then we can have something like I don't know whether. Okay, so we go to some other problem where all humans are mortal, and then we have some humans are dancers. Therefore, some dancers are mortal. What is the translation? It will be for all x human, then mortal. 2, there exists some x such that human x and dancer x. 3, we need to show that there is some x such that dancer x and mx. This is very easy actually. What we do is we just instantiate this step, we get hx implies mx, and this instantiation does not need any constraint. So, it is just 1 ui 5, we work on this. Now, this is difficult, right, because if we start doing it now, then we have to have a new variable, and the new variable will not then unite with this thing. So, this was a wrong step which we must understand. So, when we have to do both ei and ui, we do the ei first, then the ui. That is the lesson we need to learn. So, then I do the ei first, I bring y. Y is a new variable which has not been used anywhere. I just write to ei, then I can easily use this rule. So, I have hy implies my, which is 1 ui. So, my 6 will be, this is h, it can come out of it. I just write for simplification, because it is and 7. So, it is something like this, therefore 5, and then I do mode exponents and 5 6, which looks like this, and 8. Therefore, now I add these two things, hy I get from here and dy I get from here, and I just, that is what is it, 4 and 6 conjunction, and 9. I just generalize it, some x hx and dx. I am done. I just show it. So, this is how we can prove a few things here. We may take up some of these examples in the next session also. Thank you very much.